Okay, so this is May-June 20, paper 5-2, and the question number 2. The question is, a student investigates how the viscous force in a liquid varies with temperature. The student releases the ball from the surface of the liquid in a container. The ball falls as shown in the figure. The student determines the speed of the ball between P and Q and measure the thermodynamic temperature T of the fluid, mean the temperature which is measured in Kelvin. Viscosity is a term used to describe the viscous forces acting in a liquid. Viscosity has the unit Pascal into second. Viscosity eta of the liquid is calculated from the speed of the ball. The experiment is repeated from the same liquid at different temperature. It is suggested that viscosity eta is equal to He bracket E divided by KT, where E is the energy and H are the constant and K is the Boltzmann constant. A graph is plotted for Ln eta, Ln n on the y-axis and 1 over t on the x-axis. Determine the expression for the gradient and the y-intercept. So I have already solved for you. Look at this. So we will convert first this equation into linear form. So if the question contains exponential e, then we have to take the ln. So it will be ln eta is equal to ln h, and this multiply sign will be plus. So ln e, capital E over kt. And then ln eta is equal to ln h, and this power will be the coefficient, will be the multiple E divided by kt ln E. Ln E is 1. So the equation becomes ln eta E divided by k into 1 over t plus ln h by rearranging it. Now, when the equation is compared with y is equal to mx plus c, this 1 divided by t is required at the x-axis, ln eta at the y-axis. So E divided by k is the gradient, ln h is the y-intercept. So we will write here E over k gradient, and ln capital H is the y-intercept. So this is the first part. So in all question number 2, paper 5, we have to rearrange the equation and we have to separate gradient and y-intercept. Similarly, this table is already solved for you. Now the question is, the value of the T temperature and eta viscosity are given. Calculate and record the values of ln eta. So this value is ln, this is the uncertainty. So ln, calculator, use a calculator, ln 12.3. It is coming 2.509. So you can write also 2.51. Either write the same significant figure or write same number of the decimal places as number of the significant figure given the raw data. Look, this is 3 significant figure. Either write 3 significant or 3 decimal places. Now we have to write the absolute uncertainty, and the error in ln eta is equal to ln, the maximum value, minus ln eta. So we can write ln eta maximum value divided by eta, and the maximum value will be 12.3 plus minus 0.2. It becomes 12.5, and the eta itself is 12.3. So 12.5 divided by 12.3, and then ln, it is coming approximately 0.016, and we will write it 0.02. Similarly, we will calculate the ln of 9.8, which is 2.28, and then we will calculate the uncertainty. So ln eta maximum, it will be 9.8 plus 0.2, mean it is 10 divided by 9.8. So the answer is coming again close to 0.02. Similarly, next, ln 8.4, so which is 2.13, and then ln eta maximum, so the maximum eta will be 8.6 divided by eta 8.4, and the answer is coming 0.024, but when we will write it in one significant figure, it is 0.02. Next, ln 6.8, it's 1.92, and then ln maximum eta divided by eta, so it will be 7 divided by 6.8, then ln it is 0.03 approximately. Similarly, ln 5.6, 1.72, and then ln 5.8 divided by 5.6, so the uncertainty is coming 0.04. And the last is ln 4.8, 1.57. And then for the error, ln maximum value, which is 4.8 plus 0.25. So ln 5 divided by 4.8, mean 5 divided by 4.8, and then ln, this is 0.04. So this is the formula to calculate the uncertainty in ln maximum value minus ln eta, or we can write due to the ln eta maximum divided by eta normal value, because in log ln lg, this negative is represented by the division sign. Now the next part, C part, is plot the graph of ln eta against 1 over t, include the error bars for ln n. So first we will draw the points, this column at the x-axis and these values at the y-axis, because 1 over t required at the x-axis, ln eta at the y-axis. First we will take these 2 points. So look at the graph, it's already drawn for you. So we will write these points. This is the first point. This is the second point. This is the third point, fourth point, fifth point, and the sixth point. So you have to draw first these 6 points and then draw the best fit line. This black line is the best fit line, and it is represented by this arrow, mean it is labeled as BFL, best fit line. So similar to the paper 3 practical, you have to draw the best fit line from these points after plotting. Scale is already written there. Now we have to draw the error bars, mean we have to plot the errors. Before plotting the error, decide which axis has error. So look, L and eta has error, has uncertainty, mean the vertical axis has uncertainty, then we will calculate this quantity for that axis. So here for the vertical, error scale constant, number of the small boxes divided by difference of the reading. So select any number of the boxes. Suppose I selected here 10, that's 10 small boxes divided by their difference of the reading. Suppose 1.6 to 1.7, 10 boxes, the difference is 0.1. So error scale constant is coming 100. You can select 20 boxes, 30, but this is constant, you will get same answer 100. Now, multiply this error scale constant with your errors. So look at the error. First error is 0.02. So 100 multiplied by 0.02, the answer is 2. So we will draw from this point, first point, 2 boxes up and 2 boxes down a bar. Suppose this is the point, then 2 boxes up and 2 boxes down bar. You have to draw it, already drawn for you. Similarly, we will multiply the second error, which is also 0.2, with error scale constant 100. Again, answer coming 0.2. So the next point also 2 boxes up and 2 boxes down from the point, not from the line. And the next, this is 0.02 into 100. So again, approximately 2 boxes up and 2 down. So third, this one, the same, 2 boxes up, 2 down the bar. And then the next is 0.03. So we will draw 3 boxes up and 3 boxes down. Okay. So for the third, look at this. 3 boxes up, 3 boxes down, and the last two error was 0.04 into 100. So 4 boxes up, 4 down, and similarly 4 boxes up, 4 down. So the error bars are plotted, but before plotting, we will calculate the error scale constant. We will multiply by error with the error scale constant, and then the answer is actually the number of the boxes up, number of the boxes down from the point. Now we have to draw the worst acceptable line, select two extreme error bars, mean first and last. Suppose this is the first and this is the last. If we take the top of the last, then the bottom of the first, or you can select the bottom of the last and the top of the first, join them. Suppose here, I selected the bottom of the first and the top of the last. So with the red line, I joined them. So this red line is the worst acceptable line. You have to label it. So this is called the worst acceptable line. You could call it worst fit line, but it's worst acceptable line. Then after plotting these two lines with error bars, we will select 2 points for each line for the gradient. For example, this is the point selected for the best fit. This is 3.46 and 2.55. This is at the x-axis, this is at the y-axis. Similarly, select other point for this. Suppose this point is selected for the best fit again, 2.93, 1.6. And for the worst acceptable line, this point is selected for the worst, 3.8 and 2.4. Similarly, this point is selected for the worst fit, 2.95, 1.7. Don't take the point from the table. Take different points on the line, okay? Now, you have to write here, best fit line, first point P1, second point P1. So the gradient y2 minus y1, x2 minus x1. So 1.6 minus 2.55, 2.93, 3.6. The gradient is coming 1.79. And again, for the worst acceptable line, we will write its point P1, P2 separately by using the formula y2 minus y1, x2 minus x1. So this gradient is calculated. So we have to calculate the gradient of both lines by taking different point. And do remember, here is a space for the gradient. So we have to do all calculations over here. And then the gradient is required with absolute uncertainty. So the gradient of the best fit is the answer. And the gradient difference 1.79 and 1.63 mean the difference of two gradient is the uncertainty, which is coming 0.16. So which can be written as 0.02. So this is the gradient with uncertainty. And you can check your gradient by calculating the difference in the y-axis. Look, the 2.6 and 1.5 difference divided by the difference of the x-axis 3.5 and 2.8. So this answer must be close to your answer. If your answers are coming close to this answer, then your gradient is correct. But this is not the method to calculate the actual gradient, just to check, just to confirm the answer. But the actual calculation is this. Now, after calculating the gradient, there will be a part, determine the y-intercept, don't include the absolute uncertainty. So look, equation is y is equal to mx plus c, or c is equal to y minus mx. Now take the gradient of the best fit and x and y coordinate of the best fit. So the y coordinate of the best fit is 2.5, minus gradient was 1.79, and the x coordinate is 3.49. After calculating, it is 3.64 with a negative sign. So this is the y-intercept. No need to write its unit, because question says don't include the absolute uncertainty. So no uncertainty, no unit, because units are not asked here. Using your answer A, C3, and C1, determine that E and H include the appropriate units. Look, the gradient is equal to E divided by K, and the y-intercept is ln H. K is the board's given. Include the units. Now the question is, what is E? Look, E power eta is equal to H E power E divided by KT. This E whole has no unit. So the unit of eta is a unit of H. The unit of eta is given in the question, Pascal second. So we will write Pascal. Now, what's the unit of E? This E over KT has no unit. So it's equal to 1. So E is equal to KT, and the K unit already given here, joules into Kelvin. Temperature also measured in Kelvin. Kelvin cancelled. So E is the energy measured in joule. So this is the unit of energy. Next question is, determine the absolute uncertainty. The percentage uncertainty of E is equal to percentage uncertainty of the gradient, because the K is constant. So error percentage in E is error percentage in gradient. So the gradient percentage is 0.16 divided by 1.79 into 100, 8.9%. So the 8.9% of E is the error, which is coming 2.20 into 10 power minus 24, and the unit joule. Next, the last part is determine the eta when temperature is 273. The actual equation is H is equal to E, capital E over KT, eta required. H we have calculated here 0.0263, and E small e exponential, capital E calculated 2.47, 10 power minus 23, and K Boltzmann constant given, temperature given 273. After calculation, we will get this answer. So this is 0.0265, and this is viscosity, and the unit already written Pascal into second.